Mhm. Hi, everyone. Today we'll be talking about trajectory optimization for Minigolf.
Since its introduction in 1916, Minigolf has become a popular game played by hundreds of millions of people worldwide. The goal of the game is simple, to hit the ball into the hole in as few puts as possible. However, it's actually a very difficult task to master. So this motivates the construction of a robot that can do so efficiently and autonomously. Courses can have a variety of features including ponds, obstacles, slopes, and tunnels. While players traditionally hit the ball only once every time it comes to a rest, here we consider an alternative formulation where we are able to control the ball at every time step.
So we implemented our system as a multi-body plant using Drake. So our ground is an 8x2 rectangle. Our golf ball is the white ball on the left, and the hole is the black circle on the right.
To solve this, we use a mathematical program that did direct transcription. So at each time step, we have a state consisting of the positions and the velocities, as well as an input consisting of a force in the x and the y direction. Our program minimizes the running cost that corresponds to the magnitude of the force. And we have constraints for the dynamics, as well as the state constraints for ensuring that it starts and ends in the right positions, and input limit constraints.
So solving this mathematical program yields us the following trajectories. So in our simple course, as you can see, the ball travels in a straight line to the goal. And one thing that surprised us was that we actually needed a shadow ball in order to help our ball move in the y direction.
Next, we have a pond course where we have two blue circular ponds that the ball must avoid, and it does so by going above the ponds, as you can see. So we implemented this as a collision avoidance problem where the distance between the ball and the ponds has to be at least the sum of the radii.
So next we implemented an obstacle course. So as you can see, we have a red obstacle in the middle, and the ball bounces off the obstacle in its trajectory to reach the goal. And one thing that we encountered was that a problem with direct collocation. So direct collocation uses a cubic spline in between knot points, and our collision trajectory is not going to be differentiable, so it's not cubic, and that's why direct collocation doesn't work well. And even with direct transcription, there's still difficulty with collision detection in the cases where the collision occurs between the knot points.
Next, we have the slope course. So here we have tilted our ground to a slope of 0.1 in the x direction. As you can see, the ball is still able to find the straight line path from the start to the finish, as expected.
So lastly, we implemented a tunnel course. So as you can see, we have a tunnel towards the goal, and the ball passes through the tunnel before it reaches the hole. And this was implemented by using constraints to ensure that the ball and the sides of the tunnel do not overlap.
So in conclusion, our program was relatively robust to the various parameters, and it was able to find all of the trajectories in all of the 5 courses. However, if you, for example, increase n enough, it can cause the ball to do weird behavior, such as staying in place, going backwards, or taking very circuitous routes.
So some next steps for project would be to combine the various features that we showed previously into one course, and also to extend our formulation to the real world game where you want to hit the ball into the goal as in as few hits as possible. Thank you all for listening.